is a transformation of the plane where, okay, the center point goes to the center point, you're not rotating it. And if you have any other point, it goes to a point A prime such that the segment PA is congruent to the segment PA prime. So the distance from the center to the point is the same as the distance from the center to the image. That's that notion that you're really going about a circle. You're establishing the radius. The length of segment PA is the radius. No matter where you rotate it, then you're on the same circle, as long as you keep the center the same. And then the measure of angle APA prime is theta. That was the one observation you're supposed to make from the patty paper exercise. That's where it comes into play. It's part of the definition. He's called the center rotation. Okay, and there's a special rotation. We give the rotation of 180 degrees a special name. It's called a half turn. And sometimes it'll be denoted by H. H for half turn. Or you can just capital R sub P comma 180. But sometimes it's easier just to say half a turn. Half turn. So we separate out that it's special because it's also useful as well. Everyone okay? These intuitive? Okay, here's the other reason why I was so finicky before. Translation. Translations are defined in terms of vectors. Vectors also have lengths and direction associated with them. That's why we need a vector setting in the formal definition. You don't have to use the language vectors to do it as long as you know what's really going on. So I have this vector, then a translation through the vector, denoted by T sub PQ, is a transformation such that if A is any point in the plane and T sub PQ of A equals A prime, then the segments AA prime and PQ, the vector as a segment, are parallel and equal in length. This is that notion of saying, on a translation, the distance between any point in the pre-image and its corresponding image is always the same. When you're translating, it's the vector that's defining that. You're always moving the length of the vector. You have to have a predetermined direction and length given to you for a translation, and everything moves correspondingly. So once you lock that length in, everything moves the same length in the same direction. That's all it's saying. But that's why I made that big deal at the beginning of the betweens and the withins. Translation depends on the between for the definition. The other thing is, if you look at the definition, A prime, and PQ would form what? If you think about it. Parallelogram. You take the segment PQ and the segment A prime, put them all together, you get a parallelogram. So another way of defining translation is defining in terms of parallelogram. It's the same principle, it's just using the parallelogram as the means to the definition as opposed to the vector. The nice thing about this definition, though, is if you use the parallelogram, is what happens if the point you're picking is on the same line as the vector that you're using to define the direction and motion. You're just sliding along the line there. Do you get a parallelogram then, if you're sliding along the same line that the vector's on? You don't really. You do. Okay, in foreign language and mathematics, you get a degenerate parallelogram. But we don't want to bring that up. So it's not really. This is why that we use this one instead, is we don't have to deal with that anomaly. What happens if the point's on the same line as the vector is?
I think the kids might like it.
There's all kinds of other things. Well, it's kind of like a point is really a degenerate circle.
True.
If you think about it, it's still centered at the point, and the radius is 0. It fits the definition. It's a circle. You don't usually think that way. And here is, because of the direction, the length of the vector is the length of the segment PQ. The direction is P to Q. So the order of the letters in the vector tell you the direction you're moving from P to Q. So order matters. If you did the vector QP, that would be moving in the reverse direction of PQ. So the order matters. Okay, make sense?
Yes.
I don't want to dwell on a little bit. It's just giving you a flavor of where things are, so you know either if you're using the technique, you've got a sense of it. If you're building towards them, you know where you're heading towards. So you know, okay, I got to develop this and the. And there's the one you haven't experienced yet, the glide reflection. Okay, glide reflection. Capital G for glide. the notation will make sense in a second, but it's a composition of a reflection and a translation. Thus, notice the EH, comma, and the M. EH is the vector for the translation. M is the reflection line. So a glide reflection is a combination of a reflection and a translation. And M, it has to be, the line you reflect on has to be parallel to the vector that you're translating with regard to. Shorthand, okay, it looks complicated, but notice the composition. This is where function notation comes into play. You're doing composition of functions. What it's telling us here is the order that you do the reflection and translation doesn't matter. Either order will get you the same thing. There are some things with composition, remember, you change the order, you get a different answer. Glide reflection doesn't matter, as long as you meet the conditions. Either order matters. You can translate then reflect, or you can reflect and translate. It's kind of the equivalent, okay, if your feet are congruent to each other, and you walk along the line, the footprints in the sand, as long as you walk at the same pace, will basically be modeling a glide reflection. Slide, reflect. Your feet would have to be such that you're to reflect, but it's that image. If you take a simplified foot, it's that type of image is what a glide reflection is doing. So we can pose them together.
Okay.
Pardon?
You answered my question.
Okay. Where you really find these, though, if you go to freeze patterns and patterns in wallpaper and stuff, is where you really find them. Glide reflection is real handy in those type scenarios. But what it does is this really starts to show where geometry, transformational geometry, and algebra are going to start coming together through the language of functions. So we get that connection deeper down and in.
Can I ask something?
Uh-huh.
Where is all this function notation going to be introduced in the standards? Because I have a hard time believing that it's going to be in 8th grade. You can talk about it.
8th grade will probably be
Yes.
more the setting it up. It'll probably appear, you could introduce simple ones, but the more complicated, and again, this is not uniform. Notation's different. Different authors will use different notations.
But is this an expectation of the high school geometry?
It's probably more of a high school expectation because there you've got the algebra language going on. But you can still use things like, you can simplify and say R is for reflection, RO is rotation. So you can at least have a shorthand where you can set it up a little bit, but you know, all the technical use.
But are you, in the standards, are they expecting to write it in function notation, or they can get the same thing accomplished in words?
You get the same thing accomplished in words. Now, it may come down to what they finally put up. If it shows up on the test, that will determine the wording of the assessment may really drive that. But if they understand what it is, you can get by the words. In many cases, the words are the more important part. What is the meaning? If they can get that, the notation's easy. Because what's notation really for? It's shorthand for lots of words. It's a code that we use so we don't have to write a lot of words out. Just, okay, you said it, I didn't. But it's shorthand. So it's getting the words is more important than the concept down in. We can bring the notation in if needed. And that's the arbitrary part. Different authors will use different notation. I didn't do it, but a lot of books will actually use the Greek alphabet for transformational geometry to name the functions. I didn't feel like I wanted to introduce the Greek alphabet, so I went this route, which is another way of doing it. Okay, so I'm done talking for a bit. You can go explore some more. I'm going to pass out some other packets for you to do it. So wherever you are in the different packets, keep going. I'm going to pass out some other patty paper and mirror activities. And then we'll talk a little more in a little bit. I'm going to move
Maybe
this.
we could stand up.
You can stand up, move around.
Do you want me to pick up, let me see if I can find a rain break? Well, yeah, if you want to go outside, get some fresh air.
Yeah.
And I'll pass out the other ones as well.